a high-altitude world of great and fragile mountains, where people live on the edge of change, in awe and fear of a landscape that could come crashing down. For centuries, cultures have lived and worshipped with the tremors beneath their feet.
Around, I can see a white area.
Tremors that tear apart the Himalayas, while rivers wash the debris away, across a plate through the densest population in the world, into an ocean and out of the mouths of volcanoes. While cities grow and scientists try to predict the timing of the next big event. In the collision zone.
I've always wanted to see the Himalayas. I've always wanted to see the geology. I've lectured about it. I've written textbooks that include sections on Himalayan geology. But by coming here to the Himalayas, sometimes you just have to say, wow.
Canadian geologist Nick Isles is getting in a little R&R in the middle of his tectonic tour of the planet. As he cruises along outside of Kathmandu in Nepal, he's considering what he's going to see up there in the mountains where the Earth works as a machine. A machine kick-started by a continental collision after the last supercontinent broke apart.
It's one of the greatest stories in Earth history. 55 million years ago is an important marker in Earth history because that marks the end of the Tess Ocean. India, beginning its long migration northwards, collides with Asia, finally, and that's the extinction of an ocean. And those oceanic sediments, with all their included fossils, became caught in a huge vise. And they've been uplifted 2 millimeters a year over 55 million years, and they're now 8 kilometers above sea level.
It's hard to imagine that something as formidable as the Himalayan mountain range could be so delicate. They are coming down as fast as they went up.
They're impermanent features of the planet. So for all the size of the Himalayas, the biggest features on the planet, they are still ephemeral. They're being torn down by gravity, and enormous fluxes of sediment being driven out into the oceans.
Nick is going to investigate that and what eroding mountains mean to the people who live among them. Then he's going to follow the sediment stream as it gets flushed out of the mountains and down through India, out to the Indian Ocean and down to Indonesia, where it gets recycled into new land by volcanoes. New land that will turn into the world's next supercontinent. Nick is joining a donkey train in the Nepali territory of Mustang, where the evidence of the collision is everywhere.
It's a wonderful thing to see.
So we're going to see lots of fossils that were flourishing in this long dead ocean.
Nick's companion is Professor B.P. Upreti. Professor Upreti knows how to see this land as a place in constant transition. What are now mountains was once ocean floor.
So to build these high mountains, we've had to destroy an ocean, and rocks that were once below sea level are now up to 8,000 meters above sea level.
Yeah, that's true that, all these sediments that were deposited in the ocean bottom, they have been uplifted, they're squeezed up, and then, they have come up to this height.
The route to the heart of Mustang is the Kali Gandaki Gorge. For 1,000 years, traders and nomads have traveled through here, past the twisted rock faces, gnarled by tectonics. It's a land of serene beauty, but it's also prone to earthquakes and landslides. At one time, these were flat-lying sediments sitting quietly underwater. Now look at them.
It's a great example of crustal shortening, isn't it? Where you take marine rocks and you fold them and you create this high topography.
Yeah, it's the same way. You know, these rocks were deposited in the bottom of the ocean when they were laid horizontally, and then when they collided with the rocks of the Asia, then they started buckling up, and then, you know, they folded, and then now you have these mountains formed.
From here you can see the trails of the glaciers carving out the Himalayas. Down closer, you can see how glaciers work as massive earth movers. That is a Khumbu icefall down there. As the glaciers have receded, they have carried boulders and gravels and dumped them here, onto a field of ice that works as a giant conveyor belt. That is a glacial lake, dammed up by ice, ready to burst, a flood of water and sediment that will rush downstream. It's an entire system of erosion, a machine that continually works towards change. Up here, impermanence is everywhere.
This is a huge landscape, isn't it? You've been working up here more than 30 years, so why don't you take me through what we're seeing?
The place is called Kagbeni down there in that village. You can see that this is a boundary-like area between the upper Mustang and the lower, Mustang area. And here, interestingly, you have the old sediments of the ocean, the oceanic sediments, which are now converted into rocks. These rivers are flowing south from Tibet side even before the rise of the Himalaya. So these rivers, this river has cut through the Himalaya as the Himalaya was rising. So in a way, the rivers are older than the Himalayan region. And these rivers have been carrying sediments from all these areas throughout its history and bringing them to the Ganges River and then finally to the Bay of Bengal. These valleys were all filled with these sediments, and now very little is remained. That means, the power of these rivers carrying down these sediments, and one day all these sediments will be all gone from here.
So despite their thickness, they're very transitory, aren't they? They won't be there very long.
Yes, definitely. In due course of time, everything that you see, these deposits will be all gone, and only the bedrocks will be left there.
Throughout the Himalayas, one of the most impressive things you see are huge landslides and debris flows tearing down the mountains. And as soon as the uplift stops, as soon as India and Asia become locked, then gravity will win. We know that in about 200 million years' time, the Himalayas will be beveled to a low relief surface.
People have lived and farmed in Mustang for more than 1,000 years. The sediments make for fertile fields, and the landscape forms the very core of their beliefs. These are people of the Bod tradition. Bod monks meditate in caves carved into the walls of the Kali Gandaki. They crawl into the embrace of the rock itself. This village's name, Lubrak, means crag of the snakeskin. It's named after this relief on the canyon wall. People here believe that there are nasty snake spirits in the rock that will cause trouble unless they pray to them daily. Lubrak rests on a shoulder of a stream that feeds the Gandaki, but it is in the shadow of a massive boulder that will demolish the town if or when it's dislodged.
Yeah, unfortunately, the village is not in a very good place in the sense that when you have very large earthquakes, a lot of these buildings will collapse, and also a lot of these boulders will come down and, damage the building and kill people.
I can see very large blocks up there.
Yeah.
Scattered around. I can see a wide area. It's obviously been a very recent landslide. So the next major earthquake for this area will presumably send all this coming down the slope.
You may ask why these people are living in these areas. Whenever you have these kind of landslides, you have more flatter areas formed, and more gentle slopes are formed, and naturally that is a good place for farming, agriculture. So therefore, many of these areas where you have these villages, they settled somewhere in the landslide area.
These landslides only occur once every few hundred years, so there's major opportunities there for communities to occupy those areas safely until the next landslide, but it's a dangerous landscape.
So it's really no wonder that the monks of Lubrak pray for the serenity of the landscape. Everyone here is conversant on the tectonic history of the Kaligandaki. They speak of an earthquake in 1505 as if it happened recently. Of course, in geologic terms, it did. Religions have always attempted to explain why the Earth does what it does, and geologists have always tried to apply their science to the landscape to do the same thing. It's a question of perspective.
145, 150 million years or a little older.
The study of geology isn't really very old, but the cultures of the Himalayas are. So for centuries, whenever they found the fossil of a Jurassic-era seashell, they had no choice but to regard it with a degree of mysticism.
Yeah.
Well, let's see if we can excavate one of the kings
look at this
of the
beautiful
Jurassic.
ammonite. Yeah. The age of these rocks are Upper Jurassic, 150 million years to 145 million years or a little older. And during this time, the sea was ruled by these ammonites. The continents, particularly the northern...
Nice one.
Yeah, it's beautiful. This is perfect. Yeah, it came out. It's wonderful. And yeah.
So these are the kings of the Jurassic Ocean, which are now more than 3,000 meters above sea level.
Yeah, that's very interesting, when these ammonites were living in the ocean. Now they are at the top of the mountain. This is the proof that this part of the mountain was under sea at some time, about 150 million years before here.
They dominated those oceans, didn't they? In a way, the dinosaurs dominated life.
Yes,
on land
exactly.
at the same
This is
time.
very interesting. Yeah.
So is there a local name for these?
Saligram is the name that we
Saligram.
give. Saligram is the ammonite is the scientific name.
Nick and Professor Upreti are joined by anthropologist Carol Dunham, who's been studying the cultures of these valleys for 30 years. She's going to lead them to a sacred site over the next ridge. One of the most important Mustang traditions is to make sure visitors leave happy, and that prayers are said to keep the earth's rumblings at bay. The mules trudge up steep cliffs of compressed sediments. This is a land of trails connecting valleys and cultures. Suspension bridges have helped shorten some routes, but it's still best when traveling in Mustang to give yourself time. Pilgrims have passed by this shrine of stones, this stupa, for centuries. Each little rock left behind is like a coin thrown into a wishing well.
Really feel the elevation right now.
Yeah, each breath is precious. Huh?
At this time of year, the temple at Muktanath becomes a pilgrimage site for Hindus from Kathmandu and southern Nepal.
Diagrams.
Yeah.
We've seen these in every community we've visited. Now, how does a fossil become revered?
You know, these ammonites are found here in these areas. Traditionally, these ammonites are worshipped by the Hindus, and
They represent life itself, the very life itself.
So would they carry these as good luck symbols with them?
it's a symbol of God, actually. So they actually worship it every day at home. And I have these salagrams at my home, brought by my ancestors for many generations.
Some of these Hindus have walked for 2 weeks to get here, up the side of a mountain near the foot of a landslide where a crystal clear spring emerges. For these worshippers, there is a sacredness to this place, tied to the drama of the landscape and the presence of the water.
The 108 spouts symbolize all of the water actually on this planet. So today they're purifying and they're bathing as a symbol also of representing the whole world itself. Today is actually, they're worshiping the goddess Durga for the Hindus here. But before they do that, they have to bathe. They have to purify themselves so they can see clearly. And that's really where the importance of water is, which is essential to purify the mind and the body. They believe you have to do that with water.
As a geologist, I've noticed that this area is a giant landslide and the spring is emerging at the back of the landslide. Do they know that landslide could happen again in the future?
I think that there is a great awareness that they live in a very volatile place, and they see that in a sacred sense. Their worldview is one that they need to propitiate the earth spirits that they coexist with. So their response is a religious or ritual one to that, and they believe that these landslides are caused when there is disharmony and when they're unhappy, the earth spirits. What I really love is that the stories where you will look at it and as a geologist will tell one story in the striations, in the folds and the crumples of the mountains. For them, they will see a very dramatic interplay of spirits at play that is frozen there, demons and spirits that live within the rock itself.
So I come up here as a geologist and I would map this area to try and understand how the Himalayas were built, but I'm sort of missing the big picture, aren't I?
Well, I think that while you look at that incredible rich story, there is a very profound story that's invisible that they see as well within there. And when that is lost, we lose a very profound link to the earth itself.
Over the years, pilgrims have carved prayers into rock. These are mani stones, and they ask the land for peaceful passage along these mountain paths. But there are no guarantees. This path cuts through the Muktanath landslide.
We've talked about these as hazards. We've got the community down there, but basically this is how mountains are pulled down, aren't they?
Yeah, you know, this is the mountain's fate. They rise and then finally they are brought down, and One day they become flat and almost, there's no mountain left. And this is the process that happens, erosion goes on. And this is how the mountains have to come down and finally become the plains.
Flattening the Himalayas means an immense amount of material will be carried down through the Kaligandaki Gorge. The problem is that the glaciers in the Himalayas are melting faster these days, expelling more sediments and dumping a gigantic load into the river systems to the south.
Amazing amount of sediment in this river, isn't it?
One of the heaviest silt loads of any river system in the world, not the heaviest.
That's because of the Himalayan mountains, the size of them, and the fact there are glaciers eroding down into their slopes.
And they're so young and moving. They let off a tremendous amount of soil.
Claudia Sadoff is a hydroeconomist with the World Bank. She's studying how the countries that feed off the Himalayan runoff can deal with all the muck that's now carried by the rivers.
But it must cause amazing problems in all the barrages and dams downstream.
Absolutely. Any infrastructure built on the river, hydropower for irrigation, is clogged up with all this sediment level. And in order to control for the amazing flooding and movement of this river, large embankments are built throughout the system as well. And the sediment builds up between the barriers of the embankment. Good glacier water.
So that must reduce the lifetime of these dams if you've got huge amounts of sediment coming in.
Quite significantly, not only the dams themselves, which begin to have their reservoirs fill very quickly, but even the hydropower turbines are eaten up by all of the soil that goes through the turbines because there's so much soil and silt in these waters.
Now, as a geologist, I see this river carrying enormous volumes of sediment down to the ocean. It's a natural system, but you need to manage that system, don't you? What are the main challenges that arise from all this sediment that's going down the river?
Well, the sediment is so heavy that it affects all of the infrastructure that are built on the river. The river moves and it meanders. As the river washes the sediment down, the sediment builds up and it creates little eddies and it turns the river, and the river flows and is braided throughout its system, so it becomes a very unpredictable river that can be extremely destructive at times of flood.
Eight tributaries flow through the Kathmandu Valley, fed by waters from the Himalayas. This temple on the banks of the Bagmati River is the place where Hindus cremate their dead and commit the ashes to the sacred waters, which eventually join the Ganges in India. There are over 3 million people around Kathmandu. 30 years ago, there were only a few 100,000. There are few checks against growth here, even less oversight for how buildings are built and where. At times it feels like Kathmandu is a city out of control, and that's what gives it much of its charm. But it's also a disaster waiting to happen. Kathmandu is built on an old lake bed made of sediments that poured in here from the mountains, and the lake bed is on an earthquake zone. These school children take their earthquake drills seriously, right down to the fake injuries and the gory makeup. But when a major earthquake does hit here, covering their heads and running out the front door of the school might not be enough for these kids to survive.
As the city's grown very rapidly and poorly planned, it must be said, we've now got buildings on top of very steep, very unstable slopes. So the school we just visited is right on the top there, and part of the school has collapsed down slope. So if there's a major earthquake, you can imagine the results there'll be to the building.
One of the other caps Professor B.P. Upreti wears is that of an earthquake preparedness expert.
Nepal is overdue for another large earthquake, isn't it? This wouldn't be the place to be, would it?
In fact, this core part of the city, Kathmandu Valley's core part, particularly the Kathmandu city's core part, is this area. And this is going to be really a very difficult place. When you have big earthquakes, a lot of houses will collapse here. And there is a study that within 1 square kilometer of the area, there will be over 2,000 deaths, in this area. These streets are very narrow and people have very little chance to escape out, Kathmandu is a very old city. They had many such earthquakes, so they also have developed some indigenous technology for earthquake-resistant features to put in the buildings, and particularly the temples. For example, they have very good foundation, very wide foundation, even if the temples are tall, but their foundation is very wide. It's a pyramidal structure in a way. So therefore, many of these temples have survived in the last earthquake of 1934 of 8.3 Richter scale.
So I presume modern-day Kathmandu, which is growing so quickly with urban sprawl, the buildings are put up cheaply, aren't they?
That's exactly the scary thing that is happening today in Nepal, in Kathmandu, is that, the buildings are coming up so quickly and the structures are not safe. And if you are not going to make good structures, they are more vulnerable and more dangerous than the traditional buildings. Normally we say it's not the question whether there will be an earthquake in Kathmandu or not, it is when.
So we know by looking at the geology of the continents, going back 4 billion years, even more, that Himalayan-type mountains are ephemeral. So you're converting massive, impressive mountains into sediment.
These rivers feed into the Ganges. If we remember the analogy that the earth here works like a machine, then the Ganges is the transport link that delivers raw materials to the factory. But the Ganges is also the source of life for 1/6 of the planet's population. As the Himalayan sediments flow through, some are left behind to make incredibly fertile farmland. But now there are more people relying on the Ganges and what it provides than ever before. The strain on the system has become enormous. Here are some facts about the Ganges River. It's over 2,500 kilometers long, snaking from the Himalayas to the Bay of Bengal. Along its route, the Ganges sustains over 1 billion people. In Calcutta alone, near the river's mouth, there are over 5 million people, and for each of them, the river is the center of life.
The sheer volume of people that are using this water is just amazes anyone who tries to understand the different river systems of the world.
Dr. Saugata Datta teaches at Kansas State University in America now, but he grew up here in Calcutta, studying both the water and everything that gets poured into the Ganges: industrial waste, garbage, sewage, even the ashes from Hindu funerals. At the same time, babies are baptized in the river and people perform their ablutions, even though the river water itself is far from hygienic. The water causes skin rashes, infections, and intestinal problems.
getting the river water uncontaminated is out of question right now as it stands.
But I suppose the central problem is it's a holy river for many people, so how do you slowly wean them off that?
People still have this belief that the river water, the Ganges river water, is actually coming from the Himalayas and it is untainted throughout its journey or course until it gets into the delta.
How do you tell a billion people that something they believe is so sacred is filled with impurities? How does a scientist separate his work from his beliefs?
I was born and brought up in this culture. I understood the presence of the river in our society, in our religion, and it is inborn or ingrained in my family too. We still know the science behind it. We exactly know how the pollution is happening. We know that it is one of the most polluted waters of the world, but still to us, it remains as the holy water which we can use for the entire time to come for the future.
Calcutta, like India, is growing at a stunning rate. The demand for water has drawn people into the street, where they pump it up from an underground aquifer.
He's pumping groundwater from a shallow aquifer, but we're underneath this massive city. Isn't there some pollution into this?
Yes, there should be some pollution into this, but more as we closer to the city, to the river Ganges in this case, about 3 to 4 kilometers, the contamination is much lower. So this is pretty much clear water right now. They're using the water for drinking purpose for all the hotels and restaurants nearby.
And the deep water must be coming from hundreds of kilometers away, up from the Himalayas and driven down really deep in the basin.
That's true.
Himalayan water providing for all of these people. The problem is that no one is really sure how much longer the tap from the Himalayas will remain open. The glaciers are melting, and presumably one day will be gone entirely. That would be catastrophic. Meanwhile, as the glaciers in Nepal melt faster, the Ganges carries more of the sediments downstream than the watershed can handle. As freighters head towards Calcutta, they churn up water turbid with Himalayan mud.
And it's increasing day by day. Year by year, we see that right now it's about 530 million tons of sediment throughout the Ganges River per year. And in my 25 years of growing up in the city myself, I have seen more and more population is encroaching and making the channel of the river smaller and smaller.
For centuries, Calcutta has been a gateway to the sea. But now the port is in jeopardy, clogged with sediments. The ships hit bottom, and in some parts, it's impossible to navigate at all. Meanwhile, out here, south of the city where the river meets the sea, life is spent on fishing boats hauling nets through the pull of the mud, or by farming on one of the myriad bars of silt that make up the fingers of the Ganges Delta, the world's largest river delta. The sediments in the delta coalesce as small islands and then grow as even more sediments gather. But the land they form is low-lying, and typhoons can come screaming in here and obliterate everything: the farms, the channels, the livestock, and the people. Through it all, that stream of sediment never stops. Some stays, but the bulk is carried out to sea. The sediments fan into the Bay of Bengal and are swept away south. You can see them. They look like wisps of sand. What was once seabed and then was once the tops of mountains is again at the bottom of the ocean. And as they arrive in Indonesia, the sediments reach the end of the production line. They are about to be fed into the fiery furnace of the collision zone. Yogyakarta is the cultural capital of Java, Indonesia. The downtown is built around a 400-year-old sultan's palace that was knocked down by a vicious earthquake in 2006. The earthquake, which registered 7.8 on the Richter scale, leveled much of the rest of the city. Almost 6,000 people died and 1.5 million were left homeless. Yogyakarta is in a precarious spot atop the meeting place of two violent tectonic plates. And it's not very far from Merapi, the volcano that created so much havoc in the fall of 2010. Merapi is fed by the tectonics beneath Indonesia. The Indo-Australian plate grinds against the Pacific plate along these Indonesian islands, Sumatra, Java, and Bali. That's why Indonesia looks like it does. Geologically, it's known as an island arc, the surface expression of subsurface machinery right along the fault line.
This is one of the most dangerous places in the world. This is a subduction zone which runs along the whole south coast of Indonesia. And the dangerous part is when the two plates are locked. Strain builds up, and then eventually the Asian plate finally releases all that energy and pops up over the Indian plate, and that produces a large earthquake. And of course, about 100 kilometers depth, the edge of that plate is melting, and that produces the volcanoes, which lie just inland and form this spine along the whole of the Indonesian plate.
In 2004, more than 230,000 were killed by a tsunami that hit the west coast of Sumatra. In 2009, the Sumatran city of Padang was shaken by an earthquake that killed an estimated 1,300. In the fall of 2010, there were actually twin tragedies for Indonesians. First, a tsunami swamped some remote islands, killing hundreds. Then central Java was covered with ash. Merapi erupted with much more force than it has shown in a century.
The temperature around 700.
Christian Awi is a ranger who patrols the landscape around the base of Merapi and has seen every one of its many moods. He was here in 2006.
Merapi sometimes they call it good guy and bad guy. Good guy because bring good things like those boulders, stones, sands for buildings. Also for the soil, it's good. You can throw peanuts and it grow quickly. Yeah, but in the same time, destroy everything, like houses, people. Yeah.
When it's quiet, Merapi can yield everything from rocks for construction to grains harvested from the volcanic earth, which is super fertile and is the basis for some valuable agriculture. But when Merapi starts to thunder, all of the people who live around the giant volcano are evacuated. It's a cycle that repeats itself once every 5 years and makes for a very volatile place to live. The real dangers here are the pyroclastic flows, and they are intensely deadly. Pyroclastic flows are clouds of hot gas and rock that can whip down the side of a volcano at terrifying speeds, at temperatures of 1,000 degrees Celsius.
You've seen a lot of pyroclastic flows. If we were standing here when one came round that corner down the gorge, what would it look like?
I cannot think about I died immediately because the speed of the lava is about 100 kilometers per hour. We're only 3 kilometers away from up there. So what you said, no, I'm standing here, I cannot tell anything, die. Yeah.
During the 2006 eruption, 2 journalists thought they were at a safe distance. They had no idea how fast the pyroclastic flow would pounce on top of them.
We got news that they're in the bunker and they die. And day after we come back here to look for them, but because it's too thick, the material, the fiberglass is too thick, and then we have some time, 2 days, digging, and we found them. Yeah. One guy was we found next to the gate over there, the doors. It was what do you call it? Burn, like a barbecue. And the other guy was in the bathroom and was boiling, died. They both dead. Yeah. 2 days after the eruption, we found them. Yeah.
Merapi has done nasty things to a lot of people. In 1930, 1,400 died. In 1994, another 64 were killed. All is quiet on this day, though. Barely a burp on the seismograph. But on May 27, 2006, the seismograph looked like this. Merapi misbehaves often, so to keep tabs on things in the quiet times, the caretakers make a monthly trek to the summit. Just before sunrise, their headlights catch blooms of volcanic rock. Particulates swirl in the air with the sulfur gases.
This place here is the death zone of one of these subduction-related volcanoes, all because of the magma type which is pushing up underneath the volcano. It's very stiff, and most people have an image of volcanoes with red-hot lava running down the slope. It's not the case in this type of volcano. With this very stiff, magma is pushed up from the magma chamber and forms this lava dome, and we've been spending the last couple of hours wandering around this lava dome, and it gets pushed up, and it eventually collapses. And one can safely predict that in the next few months, the next few years, the whole side of the mountain will give way and there will be an enormous pyroclastic flow.
The rising sun reveals the steaming dome of Merapi. There is no looking over the lip here to peer down into a crater. After Merapi explodes, the lava congeals and covers the volcano with a cap, a form-fitting lid.
And you can see cracks around here. We've already had 2 small earthquakes this morning. And the whole side of the lava dome will fairly soon collapse.
All the signs are here: the tremors, the steam, and the heat.
This area is cracking. This area is literally falling apart. And the cracks provide conduits for sulfur dioxide and other sulfur gases, and also a lot of water vapor to come up. So these are called fumaroles, which means smoky, and he's measuring the temperature of one of these fumaroles. These are scalding temperatures. These are just a little bit below boiling, so this is quite a dangerous area. And the rocks, too, are being rotted by gas moving up through them. So this area is completely disintegrating. By walking around, looking at what's happening to these slopes, taking temperatures, we're in for a big one. This is not a place where you want to hang around. It makes me nervous because I've seen these things in action, and they're extremely dangerous. But as a geologist, I'm absolutely fascinated by the opportunity to come here and look and see what happens before a pyroclastic flow takes off.
The pyroclastic flows burst forth from Merope only a year after Nick visited the volcano's summit. Hundreds of thousands of Javanese were forced to flee as Merope's devastation spread out farther and farther. In the grand tectonic sense, Merope is part of the same machine that began in the Himalayas. And one day, the end product will roll out on the tectonic assembly line, a whole new supercontinent. This is the debris that was left behind by Merope's 2006 eruption. There were a few unlucky homeowners who had to relocate. Tourists come up here now, while they can, to tramp up and down the paths next to the farmers laden with harvest from their volcanic fields. Some people buy flowers to make offerings to the goddess of Merope. But Merope is dangerous even after the eruptions calm down, because there is always the risk of lahars. A lahar is a massive mudslide rolling with the weight and consistency of concrete. When heavy rains soak the volcanic debris left behind by the pyroclastic flows, the whole mass is dislodged. Lahars have been clocked at over 100 kilometers an hour. The government has built some retaining walls here to try to control the flow for when a lahar happens again. Just another hazard of living along the Indo-Australian plate margin. All this debris is the final byproduct of the mechanism that raised the Himalayas, caused them to shed their sediments, and then carried those sediments all the way here to be shot out of a volcano.
Well, it's a grand cycle. You have plates colliding, huge mountains being thrown up. Those mountains are defying gravity. Gravity doesn't like mountains, it wants to pull them down. Huge amounts of sediments being released. They're flushed down into the oceans, and then they're recycled in subduction zones to form new land. So it's a great epic of mountain building, plate collisions, and sediments are the thread that connects that to the future chapters of new land and new supercontinents.
And that's the point, why all of this huge tectonic activity continues. It's all about building the plates, building the land, and ultimately constructing a new supercontinent.
Supercontinents form with a frequency of about 400 million years. The last supercontinent broke up about 200 million years ago to form the modern oceans, and slowly those modern oceans are being consumed. The ocean crust is being lost down subduction zones, and we're just starting to get into the next phase of building another supercontinent. And we can predict the position of future continents with a lot more accuracy than we can next week's weather. So as a geologist, if we look into the future, we can say with accuracy that in 200 million years' time there will be another supercontinent, and it will be centered around Indonesia.
And then the process will start again. But that is 200 million years away, and for many of us, that amount of change in that vast time frame is unimaginable. But change, at least in the short term, is familiar to the people who live here. Just come visit and stay a while. Before long, you'll feel the Earth move too. The Great Rift Valley. Things have happened here that happen nowhere else. That's the underlying truth to this place. Within its walls, our species evolved, civilizations rose and collapsed. And there's an even bigger drama at play, the birth and death of oceans. It's all due to the impact of tectonics. Geologist Nick Isles is on a quest to explore its power. From the cradle of humanity to the hottest place on Earth, to the ruins of the oldest civilizations and the bedrock of some of the world's modern religions. A journey along the rift.
There's something primeval being up there and looking down into the depths of the earth. Holy cow! It's an absolutely fantastic experience, not just as a scientist, but as a human being.
This is the East African Rift, one part of the Great Rift Valley that stretches from Mozambique to Turkey. It's a special place for humankind. Embedded in these cliffs, packed between layers of volcanic ash, is the story of our origin.
The rift system is our natural home, as it were. That's where humans evolved. We developed in association with volcanoes and faults, earthquakes. So it's a great view of where we originated. The whole landscape is covered with great thicknesses of ash, which is a good thing because those ash layers entomb the remains of early humans and their ancestors, and they provide precise marker horizons of time.
Ever since Darwin suggested that humans share common ancestors with African apes, scientists have searched for further clues. The only place they found fossils that link directly to modern humans is in this long, narrow valley. The intriguing question is why. It's geologists who think they've found the answer. Canadian geologist Nick Isles seeks to understand how human history is linked to the geology of the Great Rift Valley. He begins his journey in Kenya to explore the theory that the rift was the catalyst for human evolution. He meets German geologist Martin Trout. Trout has spent his career dating sediments and cross-referencing them with evolutionary changes. He's concluded that each step in our evolution coincided with the appearance or disappearance of large lakes in the Rift Basin.
If you have major events in human evolution occurring at the time where we have large lakes everywhere, that's probably an evidence for that there should be a link between climate and environmental changes and the evolution of early humans.
So if large lakes were the key to human origins, what happened when these lakes disappeared?
When they've disappeared, probably they have to change dramatically the strategy to find food in the environment. But these lakes, they reappear in cycles, and so that makes them very good for humans to survive as they are generalists.
The frequent environmental changes drove our ancestors to evolve ways to better adapt to new landscapes and diets. Here at Kariandusi, Trout has studied a particular lake deposit called diatomite that dates back 1 million years.
This is actually a lake sediment. It consists of millions and trillions of skeletons from little plants.
As the lake dried up, early humans left traces of their lives, hand axes embedded in the walls of the gorge.
So what uniquely defines a Chilean hand axe?
The Olduvai tools are just very, very simple, round-shaped kind of hammers. Nothing else. And these ones are really for cutting meat.
We see the development of stone tools about 2 million years ago and the development of human brains. And to me, that's not coincidental. You've got to find the rock. You've got to know what rock type make good tools. You've got to communicate that to others. You need a social organization to manufacture those stone tools. To me, that was the first industrial revolution because it required manufacturing on a huge scale.
To understand why this revolution happened, it's necessary to delve deep into the tectonic story of the Rift Valley.
Geologists come to the East African Rift because it's the largest tear affecting any plate on the planet. It's a huge wound which is opening up.
That wound arose because the African plate lies above a huge plume of magma that's slowly melting the crust, causing it to stretch or rift. On the edges of warmed rock, high shoulders rise up. In the middle, the floor subsides, forming a rift. "3 million years ago, repeated rapid swings of climate from wet to dry caused huge lakes to form and suddenly disappear. Combined with frequent volcanic eruptions and earthquakes, our ancestors faced unbelievable odds. For Nick, it's part of a greater truth that he's exploring, that the Great Rift Valley is unique. Things happen here that happen nowhere else. One of the great findings of geology over the past 40 years is that oceans come and go as supercontinents form and break up. But how do continents split? And how do new oceans form? To find the answer, Nick comes here, the Afar Depression in Ethiopia. The Afar Depression is one of the most dramatic landscapes on Earth. Few people live here, and even fewer visit. But to geologists like Nick Isles, it's Shangri-La.
This is a fantastic place to be because we're driving along the middle of the East African Rift, where the African plate is literally being torn in two. And Africa is over here, the Somalia plate is on my right, and they're moving apart. And the rift between the two is slowly subsiding.
This tectonic process has been underway for 30 million years. But the Afar is so remote that its significance has eluded geologists until recently. For Nick, it's a once-in-a-lifetime opportunity. His ultimate destination, a volcano called Erta Ali, or Smoking Mountain in the local language. To get there, he must first cross the Danakil Desert.
This is a serene landscape. These are enormous lava flows which have come down from the margins of the rift from these big volcanoes.
very fluid lava extending for many kilometers down slope. But here they've been broken up by faults. It's absolutely amazing. It's just geology happening before one's eyes.
The next morning, the tarmac ends. Nick's transported back in time. Salt is the livelihood of many tribal people living in the Danakil. It's mined by hand, packed on camels, and sold in markets a 3 days' walk away. On some days, 1,000 camels will plod by here.
Camel trains have been taking salt from the Danakil Depression down there below sea level all the way up to the highlands for centuries, and I've just seen it. It's as if the modern world never existed.
Next stop, Nick goes even further back in time, to the dawn of life. This is the Dalal crater, a volcano whose summit is still below sea level. The crust here is incredibly thin, the magma close to the surface. What's unique about this place is that this volcanic activity is interacting with very thick salt deposits. Early life may have thrived in environments like these 4 billion years ago.
First to arrive are the hot fluids migrating up above the magma. And then puncturing the salt are these beautiful little industrial pots. The hot water's coming out, bringing sulfur-bearing minerals, beautiful colors, and there's bacteria, very simple, blue-green bacteria in there that love these hot waters.
These simple, colorful bacteria are Earth's oldest life form.
And this may be a glimpse into early Earth. This whole area is underlain by what's referred to as a mantle plume, which is a huge mass of red-hot plastic rock which is rising up from the mantle, impinging on the base of the African plate and pushing it apart, splitting it into two. As we go further out in the Afar Depression, we go below sea level. And at the moment, the ocean is only prevented from flooding into this area by volcanoes. Eventually, they will subside under the great weight of all the volcanic rock, and the sea will burst in here.
In 2005, volcanic eruptions and earthquakes rocked the Afar Depression. Fissures opened up, and large flows of black basalt lava flooded the landscape, creating crust of a new ocean floor. Nick crosses paths with a group of scientists from Britain, trying to explain why that new ocean is forming here. They use seismometers to track the numerous earthquakes that hit the Afar. Each quake corresponds to the injection of molten rock into the crust, slowly splitting the continent in two.
So how many of these do you have across the Afar?
In total, I think there's somewhere around 45, but that's combined between UK seismometers and US seismometers.
The moment of truth.
In this particular area, the main axis of the rift is Ertale and Tatale volcanoes. And then it steps dramatically to the west and then further to the south. So there's a well-defined rift axis.
So you're right at the beginning of this whole new ocean.
Yeah. Along the areas where the rift axis steps dramatically, there are aligned cones perpendicular to the axis of the rift. So it's possible that the strain is transferred by volcanic intrusion rather than transform faults like we see in mid-ocean ridges.
With each geologic event, the Afar Depression evolves. But seeing the process with eyes instead of instruments requires getting to Ertale. Easier said than done.
Well, this is the road up to Ertale. We're actually crossing the lava fields. It's just a simple track. This is a vehicle that's broken down. It's lost a bolt out of the steering, and we stopped to help out. And ironically, we just passed a camel train taking grain over to Eritrea, and they're making much better progress than we are.
Nick is now 20 kilometers from the volcano. His guide, Solomon Berhe, takes him to meet some remarkable people in a village called Ali Abdallah.
So what's it like living on a huge sea of lava?
እንዴት ነው እዚህ በጣም ድንጋይ ነው እንዴት ትኖራላችሁ? It's very difficult, tough life. They have been here for 10 years. This is a station for their family. But they move their animals from place to place.
Do they ever consider moving away from this area?
When there is rain, Artale area, there is grass. So he takes his goat and his camel to that area. They discovered it's not dangerous. Now they believe it doesn't flow. So that's why they live here.
I'm amazed that people can survive here, living literally on lava. There's no soil. We've seen children running around in bare feet on hot rock. It's absolutely amazing. This is their home. And there have been people living here for millions of years because this is where some of the earliest pre-hominid fossils have been found. So there's a continuity of life here in an extremely arid, hostile environment.
Finally, Ertale. It's not very high or impressive because it's a shield volcano. Shield volcanoes don't explode. Instead, the lava is very fluid and flows like blood across the landscape. The truck can't make it to the crater. The gear goes on camels. Nick and Berhe go on foot.
So do you get excited every time you come up?
Oh yeah, I do. Except hardship.
That's amazing. Look at it. A bloody great sea of lava. Incredible. Enormous volumes flooding out over into the depression all the way through here.
Yeah.
Amazing volumes.
Fantastic.
Wow.
You know now, Dr. Nick, I'm going to take you to the old crater where still it has a smoke.
So this is all the source of all the grey lava flows, the ones that come out of it.
It came out from this one.
Oh. It's another crater, but
Yeah, it's
dead. So So it's just degassing now, right? It's sitting there doing nothing.
It is, yeah.
This is the final stage when a volcano dies. So it's bringing up sulfur, and we get this tremendous outgassing. These gases are actually cooking the rock. This was hard lava just a few years ago, but it's now really rotten. And it's been rotted by gas coming up through it. So this is a very important stage of volcanic activity because it's bringing up precious minerals.
Erta Ali's other crater is still alive, and active lava lakes are extremely rare. There are only 4 in the world.
This is the holy grail for me because I've never seen fresh lava in a lake before. So this is Volcanoes Central.
The 30-minute hike to the lava lake is dangerous. Berhe wants to avoid the heat of the day, but still get there before sunset.
This is pretty unstable, isn't it?
Yes, it is. Especially at dark. It's very dangerous.
Yeah, and now we're on one of the main lava flows. This is interesting here. We've got this younger, dark-colored flow sitting on top of that lighter brown-colored one.
So you mean the brown is older?
Yeah, see the black one sitting on it?
Yeah.
The darker the lava, the more recent the eruption that spewed it out.
This is like walking on thin ice. It looks quite solid, but it's actually just a very thin skin, which was insulating red-hot lava streaming through as tunnels underneath and feeding the fronts of the flows. So you've got to be very careful moving over these in case you drop right through into one of these open tunnels. Holy cow, will you just look at that? That's incredible. That's amazing. It took 3 days to get here, 40-degree temperatures. How many dozen bottles of water? And it's worth it. Wow. You see the cooled skin and the upwelling magma between them. It's like plate tectonics. Well, geologists are always looking for small-scale examples to explain bigger global picture. And here we've got a perfect example of plate tectonics on a small scale. And we can see dark grey rafts, which are like continents, separated by bright red rifts where new magma is coming up, forcing those continents apart. And what's happening every now and again are huge bubbles of sulfur dioxide coming up from depth. That's the closest we'll come to actually looking at the Earth's mantle. There's something primeval being up there, and we're looking down into the depths of the Earth. It's an absolutely fantastic experience, not just as a scientist, but as a human being. That's amazing.
What Nick saw on a microscale in the lava lake is writ large across the Danakil.
I've seen a lot of rocks and landscapes around the world, but this is the clearest example I've ever seen of this sort of tectonic setting. We can see these long, dark cracks down here running into the distance. Through that little volcano, there's a crater there, and then the big guy in the distance. And this is marking the edge of the African plate on my left
and the Somalian plate on the right. The two are moving apart as a result of magma coming up along these fissures, which is pushing the plates apart. It's absolutely fantastic.
In 10 million years, the expanse in front of Nick will be transformed into an ocean. It's a testament to the power of plate tectonics. Nick now leaves the Afar and goes north through the Ethiopian highlands to explore how the rift's geology inspired some of the world's first civilizations. This stream will widen into one of the most fabled rivers in the world.
The Nile River is a direct product of precipitation over the Ethiopian highlands, and that's been likened to the water tank of Africa. Rainfall flows to the west and then north. So without the rift, there would be no Nile River.
From Ethiopia, Nick follows the Nile into Egypt. To both the east and west is desert, but through this valley oasis came early humans migrating out of Africa. 6,000 years ago, this valley saw the beginning of one of the world's first civilizations. It was a society shaped by the river, dependent on its seasonal floods.
Over there you see the Nilometer for the measuring of the water by the steps which are found in the Nile meter going down to the water, and the marks in the wall.
Measuring the height of the river enabled the priests to predict potential flood levels and to gauge what land could be cultivated.
So they could predict the floods from this. If it was high, it was going to be a good flood.
Yes.
Everybody was going to make a lot of money, they could tax more.
Yes.
If it was low, then they were going to have a hard time, and you couldn't tax them as much.
Exactly. Because this is the main source of the income for the priests and the king.
And it's from this simple instrument, as crude as it seems, that they got their power.
And that power was expressed in huge stone structures.
We see this beautiful evolution in man's relationship with the planet, in winning stone, working stone, and building these lasting monuments. So I refer to ancient Egypt as the second industrial revolution.
The power of what was called Upper Egypt rested here, the Temple of Luxor.
This is my favorite statue in the whole of Egypt. It's one massive block of black Aswan granite depicting Ramses II. Running throughout it are these beautiful dikes of pink granite. It's a wonderful example of granite as sculpture. These columns are huge, aren't they? And they resemble giant papyrus.
That's right.
The columns represent papyrus reeds, the symbol of Upper Egypt.
Now, how on earth would they have been built?
Blocks, mud bricks, blocks, and so, step by step, until arrival to the end of the column.
So they would have hauled the blocks up, put it on top of the previous one, up a ramp made out of mud bricks.
You understand?
So at one time, all this would have been full of mud.
That's right.
And then they take the mud out and start carving the columns down.
That's right.
You know, I've been looking for many years for depictions of the actual people that sweated and toiled building these temples. And here it is at last. There's a central pylon, and you can see people climbing up ladders. There's teams of people with ropes, pulling on the ropes. And here at last is a picture of the very people that built these temples.
Ancient Egypt was so firmly rooted in the detailed knowledge of the region's geology that it's been called a state of stone. This sandstone quarry has been worked for thousands of years.
To be honest, as a geologist, I find this rather dull and boring. I can't find sedimentary structures, fossils, or color variation that tells me about how this rock was deposited. I know it was deposited in a very shallow seaway with an abundant supply of sand. But that's the point. What I find uninteresting as a geologist is a delight to the stonemasons. They could easily carve this into flat slabs for the front of the temples, and what's more, it was perfect for developing the art of hieroglyphics.
The most prized monuments from ancient Egypt are obelisks, made of a specific red granite found near the city of Aswan. Everyone from the Romans to Napoleon spirited them out of Egypt. One obelisk, however, never made it out of the quarry.
This is the unfinished obelisk at Aswan, and they were going for a world record when they were trying to win this one out of the quarry.
This 1,100-ton piece of red granite is 42 meters long, a third larger than any obelisk ever erected.
Well, the Aswan granite is naturally fractured, and like carpenters working with grain in wood, the Egyptian stonemasons were very good in utilizing these giant fractures, and this beautiful smooth wall is a fracture that runs the length of the quarry. You can still see surveyor marks on the side walls.
In this deep trench that runs along the side of the obelisk, we can see how they would have released this. They would have lit a fire along the length of the trench, heated the rock up, throwing water on the heated rock, which would have fractured it, and then they would have used dolerite. This is a mole, much harder rock than a granite, and they would have used that to excavate all the softened rock. And by all accounts, this represents about a year's work. But of course, it was all for naught. Well, this is the reason why the unfinished obelisk is still sitting in the quarry. These are cracks that appeared just when they were starting to lever off the obelisk. And normally they were pretty good at winning out huge blocks between joints that affect the whole granite system here. But because it was so long, they'd actually stepped over some joints and they suddenly opened up. So really, they were defeated by plate tectonics.
What's remarkable about the ancient Egyptians is not just their expertise in stone building. They were also the first to develop a highly sophisticated religion based on a belief in eternal life.
It's an interesting example of where a new science, in this case geology, has arisen out of a religion and the need for immortality and lasting memorials. So it's a profound change in the way man related to the planet. They were burrowing away in the universe mentally in terms of their religion, but they're also burrowing away in the ground and profoundly changed the way man views rocks. So they developed the first geological maps 3,000 years ago. They're very accurate. They developed mines. They sent out huge prospecting parties, 10,000 people strong, to find minerals. It was all out of the need for immortality.
Nick says goodbye to Egypt and travels to a section of the rift where volcanic activity along the floor of the sea has caused the valley to spread so much that it's formed a new ocean.
This is a young ocean. It will widen. It's pushing the Arabian plate behind us away, pushing Africa the other way. And eventually this will grow up into an adult ocean, like, say, the modern Atlantic Ocean. So it's that intrusion of volcanic material all the time
which is the driver for plate tectonics.
From here, Nick enters the Dead Sea Rift, a deep-sided valley where the Arabian plate slides past the Sinai-Israel plate. It's a geological time bomb that has already leveled ancient cities and threatens to do so again.
This is classic Lawrence of Arabia country, classic topography. This is the Arabian plate, which has been deeply bitten into by erosion. These rifted plate margins, where one plate is moving past another one, are extremely dangerous areas because they produce large numbers of earthquakes. And this area has been densely settled for thousands of years. There's a rich historic record of earthquakes. So this area is of real interest to geologists and archaeologists looking at the relationship between large earthquakes and civilizations.
Nick teams up with one of the top scientists in the realm of earthquake study, Israeli geologist Shmuel Marco. Marco combines archaeology and history with his own geological findings in order to build a database of earthquake activity in the Middle East.
These are 2,000-year-old inscriptions.
Yeah, Nabatean inscription.
They've come to the fabled city of Petra. 2,000 years ago, it was the trade capital of the Nabateans. Goods from as far away as China and Rome passed through here. But it's the Nabateans' extraordinary use of rock that the scientists find intriguing.
So this grand entrance into Petra is along a very narrow crack.
It's a crack that was widened by erosion of water.
The Sik, as it's called, was originally a small fracture formed when the Arabic plate split from the African plate.
So that Dead Sea Rift was key to the formation of Petra.
Yes, it formed the relief here, the topography. And without this, you'd have a flat surface as it was before the rift formed.
So it's truly a tectonic city. The grand opening.
Yeah, this is the first impression that you get when you come to Petra. They took advantage of a crack in the rock.
Around 500 AD, Petra was abandoned. All that is left today are the palaces, temples, and tombs carved into the rock faces. What was built between the valley walls is a mystery. Was it destroyed by earthquakes? Ancient cities are often built on the remains of earlier structures destroyed by war, fire, or some kind of natural calamity. Fallen columns, bulging walls, and rubble provide clear evidence of ancient earthquakes. These are the ruins of Petra's Grand Temple.
So the trick is to positively identify earthquake damage, but also accurately date it, isn't it?
Yes, for example, here, look at this. We know that the building was constructed in the Nabatean period. The columns are so robust that there is no way that they fall naturally without a horizontal push. We have been recording earthquakes using modern seismographs only in the past century or so. This is not enough time for studying earthquakes because the recurrence is much longer than a century. So in order to study earthquakes prior to this instrumental period, we use fallen buildings. Cities are a treasure for earthquake geologists. And these columns buried coins that were dated up to 361 AD. And coins were found also in Aqaba. So we know that the earthquakes affected Aqaba and Petra at the same time. And we combine this with historical reports from northern Israel and northern Jordan and Syria. And we know that it was the May 19th, 363. We don't know the time of the day, but we know the date. That's very rare in geology. And that's an advantage to using history and archaeology combined. So the widespread damage really shows that it was a major earthquake, probably magnitude 7 or above. If it happened today, it would be disaster.
From Petra, Nick goes north into the land of Canaan, the modern-day Israel.
Well, I'm currently floating in the Dead Sea, 420 meters below sea level. One of the saltiest places on the planet because we're along the Dead Sea Rift. There's Israel over there, there's Jordan over there on the other side of the rift. They're both moving northwards, but they're moving at different rates. So this area is slowly being pulled apart.
The Dead Sea has been much higher in the past. Thick sediments, now exposed, are a treasure trove for geologists.
So these are bottom deposits of an ancient Dead Sea, but we're much higher than the modern level.
The lake, the Dead Sea, which is a small lake now, extended for 220 kilometers from the Sea of Galilee all the way to the middle of the Arava Valley.
This is the Lizan Formation. It's where Shmuel Marco began his research on earthquakes as a graduate student. And he's got evidence to show Nick of the Dead Sea's violent past.
So it's pretty unusual to get a nice record on land, isn't it?
Yes, it's very unique.
These are very fine laminations. Now, I presume you've measured the thickness of each one of these all the way down.
Yes, yes, we have very, very detailed record of every little variation in the deposition. We see white ones and dark ones.
The alternating layers record seasonal flows into the ancient Dead Sea.
This fine lamination is there undisturbed unless you shake it. And during earthquake, this nice layering is disrupted and sometimes broken, and it's deposited again. So when we look up the section, we look for layers that are disrupted.
In this rock face, which records the last 50,000 years, Marco has found disruptions representing 30 separate earthquakes.
We show with this record that earthquakes come in clusters. So we have 10,000 years of intense activity and then 10,000 years of less intense activity.
Marco's conclusion? The 21st century will be very seismically active.
The Earth's surface is shifting all the time. There's no one part of the Earth's surface which is stable. Most places are moving at several centimeters a year. There are earthquakes globally, but the big issue is what risk do these pose for modern cities, modern people?
The region is rich in historic and tectonic events. Some are recorded in biblical texts, some by the ruins of past cultures. All are recorded in the geology. Masada. It lies right along the edge of the Dead Sea Rift, 400 meters high, surrounded by valleys. A setting which made the fort a near impregnable stronghold for Jewish rebels fighting the Romans in the 1st century AD.
So this is a Roman camp here, another one over there.
Up on the hill.
Instead of surrendering, the Jews committed mass suicide. But there's a geological subtext to that history for Nick to see. The fort was originally built by King Herod, but abandoned when the city was largely destroyed by an earthquake.
You've got 3 lines of evidence regarding an ancient earthquake, don't you?
Yes, we have archaeological evidence in the form of fallen walls. All the walls here used to be part of the storage area for King Herod. You see the courses still aligned, but fallen. They fell in the earthquake of 31.
Traces of the same earthquake are recorded in deformed sediments found in the Lizan Formation, providing geological, archaeological, and historical evidence of the timing of the event. It took 3 years for the Romans to breach Masada. The earthquake would have taken mere seconds. The destruction of Masada was matched in severity by another earthquake that flattened the ancient city of Hippos.
So how do people explain earthquakes then?
It was the wrath of God, obviously. I think each place has its own myth and legends about earthquakes. Although only in the late 19th century and in the early 20th century did people realize that earthquakes are actually a rupture of the crust of the earth.
The Dead Sea Valley illustrates the scale of these events, each earthquake further tearing the rift apart. It looks innocuous, but the Jordan River flows right along the edge of the Israeli and Arabian plate boundaries. The scene may seem peaceful, but the river divides some of the most disputed territory on the planet, both now and in the distant past. This ruin was once a Crusader fortress. Its history tells both of war and geology.
So this wall is excellent evidence of an ancient rupture along the Dead Sea Rift.
Certainly, the wall was built straight here. And after an earthquake, we find it over there. So we know exactly how much it moved, and with combination of history and archaeology, we know exactly when. We know that the foundation stone was laid in October 1178, and the earthquake was May 20, 1202. And it's incomparable to any other earthquake that we are aware of.
The 1202 earthquake was reported as far away as Iraq, Sicily, Turkey, and Egypt. It was the largest earthquake to hit the Middle East in the last 3,000 years. And the fault system lies directly below this fortress.
So you and I are standing on completely different tectonic plates, aren't we?
Yeah, you are on the Israel or Sinai plate, and I'm on the Arabian plate.
Now, this hasn't moved subsequently. Does this mean that the two plates that you and I are standing on are locked?
Probably, yes, yes. Our estimate is that about 4 meters of slip are missing. It's a lot. It's like an earthquake of magnitude 7 point something. It's a major one. We are missing a major earthquake here. And it will certainly strike one of the major cities.
There's a consensus among geologists that there will be another earthquake soon.
All the large cities of the region are within the damage zone of potential future earthquake. And earthquakes would not discriminate. They will hit Syrians, Israelis, Jordanians, Palestinians, Lebanese, all the same.
The East African Rift nurtured our emergence as a species, saw the first civilizations. Now, it's a threat to the many cities along its length. Understanding the history and dynamics of the rift is fundamental to understanding our past and our future. Nick's journey ends on the coast of the Mediterranean Sea. And like everything else he's seen, it too confronts unstoppable geological forces.
The African plate is being driven north several centimeters a year up against the backstop of Europe. So what we see now as water will be dry land in 10 or 20 million years' time. One of the big revelations in geology has been understanding that the Earth's surface was not made the way we see it today. It's undergone these profound changes because oceans have a life cycle. They're born, they widen, and they die.
To people who can read the rocks, the Great Rift Valley illuminates the power of that tectonic cycle better than any place on Earth. There are places in the world that are poised to explode. Hotspots that radiate unimaginable energy. A world created out of fire and ice. Where power comes from the bowels of the Earth.
Strongly vertical rocks here.
Where layers of rocks are turned topsy-turvy by tectonic tension. Where that tension has been released into a vertical land of glacially carved pinnacles and geologic wonder. Across the Eurasian plate, tectonic Europe. A lonely, empty research hut on the southern coast of Iceland.
Yeah, this is quite an emotional moment for me because we spent a lot of time here back in 1977. This was our home from home when we were working on the glaciers.
Canadian geologist Nick Isles has not been here for a very long time.
And that was my bunk down there, and this would have been full of people with wet gear hanging from the roof, probably a fire out there trying to get some warmth.
These days, Nick is a professor of geology at the University of Toronto.
When we were working here, the ice was a lot closer than what it is now.
For geologists like Nick and his good friend from Reykjavik, Tristan Hughes, Iceland is a wonderland.
If you go over the ridge, the glacier's gone back a long way now.
It's a place where the effects of tectonics are palpable, and where the relationship between volcanoes and glaciers is always changing. Now, in the grand scheme of things, Iceland is small, and to some, it may even have seemed inconsequential. That all changed in the spring of 2010. Eyjafjallajökull started spewing ash for the first time in 200 years. And the position of Iceland in the world's consciousness went from this to this. The ash cloud was dense enough to cancel flights around the world. The column went as high as 11 kilometers into the sky. There are particulates in the ash that could choke the air intake of a jet engine. It was the biggest disruption in air travel since 9/11. Icelanders are forever aware that the next big one could happen any day. In Iceland, the glaciers sit on top of the volcanoes like lids on cooking pots. Every now and again, the pots boil over and the lids lift off, and kaboom! Floods, ash, and lava are everywhere, exploding with enough force to twist these steel girders from a highway bridge like pipe cleaners. So the glaciers are the regulators of volcanic activity. Myrdalsjökull, where Nick and Kristen are heading, is a relatively small Icelandic glacier. But don't let that fool you. It's still formidable because it covers a nasty, simmering volcano called Katla.
And you can smell the sulfur, so you know there is a volcano underneath here.
It's an example of a dirt cone.
Yes.
which is volcanic ash.
It insulates the
Yeah. So if you dig away at the surface, there's ice.
Ice underneath.
Underneath. So it's not a cone of solid ash. It's
actually
just
quite
skin.
thin. Yeah, it's a skin.
Yeah. We've got to remind ourselves all the time of that. There's an active or quiet volcano right underneath the ice.
Well, maybe not so quiet.
It's just simmering.
Simmering, ready to go.
If that monster volcano Katla went off, the explosion would be an estimated 10 times stronger than Eyjafjallajökull. But luckily, at least for now, the glacier over Katla has been keeping a snug cap on things. Glaciers and volcanoes. The relationship between the two would seem highly incompatible. But it's because Iceland is still young and still cooking. It's only been here for about 8 million years. Iceland is also part of the ocean floor, pushed up to the surface by heat. That's why Iceland is so important to science, because there is nowhere else where geologists can walk across the landscape and at the same time study how the seafloor is spreading due to magma coming up. And magma is the fuel of plate tectonics.
There's nowhere stable on the Earth's surface today. Everywhere is moving. I think it's important to bring people out into natural landscapes and explain how that landscape got developed.
In some places, you have to watch where you step. Those mud holes are scalding hot, and the crust around them can be as thin as paper. But in the midst of all this potentially dangerous ground, Icelanders have spotted opportunity.
This is basically steam. This is a high temperature hot spring area, so it's steam that comes from the ground. They use that steam to heat up cold groundwater, which they then pipe to the towns. And we are going more and more into generating electricity with geothermal steam rather than hydro.
And presumably there's an unlimited supply of geothermal energy.
Yeah.
A renewable resource, courtesy of plate tectonics.
For the next 1,000 million years, at least.
Yeah. Now, presumably the next lava flow is going to wipe the plant out.
Yeah, possibly, very possibly.
Or a fissure might open up below it.
And this is simply the risk you have to take. We are living on a volcano. It's a very interesting town here we're driving through, Hveragerði.
Icelanders understand that there is a risk to simply living in this landscape. Sometimes it's right under their houses.
Last year we had an earthquake here, 6.4 on the Richter scale, and many of the houses were damaged so seriously that they weren't usable anymore.
So there's swarms of earthquakes?
Yeah. And the steam you see up there in the mountain, these are actually new hot springs created in the earthquake because there is a displacement. Cracks are formed in the bedrock.
In this town a year earlier, none of those steam fissures were even here.
They are often created in the cellars of these houses, in their front yard. It can be a problem sometimes.
Iceland literally rides a plume of magma above the spot where the Eurasian tectonic plate meets the North American plate, right on top of a staggering amount of geologic power.
So, Nick, this is an excellent example of the raw energy we are tapping into underneath here. This is a borehole which is flowing now, and it produces 19 megawatts of energy.
19 megawatts is roughly the same amount of power generated by 4 electric locomotives. When they first tap one of these boreholes, it explodes with so much force that engineers have to let it blow off steam for weeks until they can cap it with a high-pressure pipe.
So this is only happening here because we're near the edge of the plate. It's very thin, we're close to the mantle source, and the rocks are really fractured, so the water glides down and it comes up superheated.
Yes, yes. And if we wouldn't have a muffler on this, we wouldn't be able to stand here. The sound would be so we'd lose our hearing in seconds.
All of this power is here because magma is coming out of the entire length of the rift all the time. It's where plates are being built. It's like two conveyor belts moving in opposite directions, pushing the plates apart. Because Iceland's rocks are on the surface and right on the plate boundary, it's the perfect place to see how plates grow. This place is called Thingvellir, and that path down there runs right along where the plates meet.
So could you automate the network that you've got?
Yeah, we have
Professor Freystein Sigmundsson takes regular measurements here. He's keeping track of how fast the plates are separating.
the rate of plate movements here in Iceland is about the same as the rate of the growth of your fingernail. So when we come back after a year, we can measure the spreading. In Iceland, this is 2 centimeters per year.
And we're looking out across a big rift valley, which is the boundary with Europe.
Yes.
And you're measuring the rate at which North American plate is being pushed to the west.
Yes, exactly. Regular measurements have been conducted here since the acceptance of plate tectonics in the 1960s.
So if it wasn't for the Icelandic plume, all this would be underwater. This would be part of the North Atlantic Ridge and we wouldn't see it.
Yeah, we would be 3 kilometers below sea level.
So we are at the leading edge of the North American plate. And if we just go over there, over the ridge actually.
It's only a 5 minutes drive to Europe here.
Wow.
Iceland exposes a process that is going on continually along the bottom of the Atlantic Ocean. The floor is always spreading along a mid-ocean ridge.
A moonscape would be the word to describe this.
Yeah, it's
environment.
a landscape which otherwise you can't see because it's underneath the ocean.
The only place where the ridge comes up for air is Iceland. So Nick is here because he can actually see what the geology looks like at the bottom of the ocean. He can see where surface eruptions are the same as what happens on the seabed.
As we knew more about the ocean floor, as we knew more about the center lines of the ocean, such as what we see in Iceland, where new crust is being added, and that addition is pushing the plates aside. As that information got added to geology information, it became completely clear that the continents had migrated as part of plates.
The plates have their own system of movement. They come together, they break apart. The Earth's last supercontinent was Pangaea. For a long time, it remained intact, and then the plates broke apart, and we wound up with the continents and oceans we know today. The Eurasian plate stretches from Iceland, where it is born, to the Alps in Switzerland, where it smashes into Africa. Eventually, Nick will make his way down there, but not yet. There is still way too much stuff going on in Iceland. Olafur Eggertsson is one of those Icelanders who has taken full advantage of the cheap local power. He's been tapping into a volcano for years.
Yes, near Borholan. So here we have the borehole.
This is a source of geothermal heat.
Yes. And exactly 20 years ago he drilled this hole. And you can see the water that comes out of it is 66 degrees.
Olafur uses the geothermal water to heat his whole farm, barns and all, while tapping the force of a glacial waterfall to run an old turbine that his grandfather built in the 1920s.
So any surplus energy that you generate gets put back into the national grid, is that right?
Umframframleiðsla hjá þér færi þá inn á netið. Já.
Ég sel rafmagn og ég kaupi rafmagn. En þetta svona svolítið jafnvægi og símareikningurinn minn hann hærri en rafmagnsreikningurinn.
When he is producing more electricity than he needs, he sells it to the grid. When the farming operations are the most demanding for electricity, he has to buy off the grid, but it evens out, and what he pays for electricity for his whole farm, this is a big farm for Icelandic standards, it's less than his phone bill. So.
Unfortunately for Olafur, his cheap heat and power come from Eyjafjallajökull, the volcano that exploded. It's right behind his farm. Olafur snapped this picture just as he was being evacuated. The thing about Icelandic volcanoes is that they hit with a triple whammy. When one starts to bubble, it melts the ice on the underside of the glacier, and that creates the risk of flash flooding. That alone can be devastating. But then the ash starts to mix with the water. The pressure of the eruption lifts the glacier, and fast-moving walls of debris go speeding into the valleys. Icelanders call these jökulhlaups, which literally translates as leap from a mountain. Finally, once the glacial lid on top of the crater has melted, a full-on volcanic eruption happens, showering the surrounding countryside with ash. The 2010 eruption covered farmers' fields with 20 centimeters of ash. It has rendered them useless until the ash can mix with the soil, making the fields arable again. That could take years. In the ruins of a centuries-old stone shepherd's cottage, a subterranean vent into the kitchen is still open. A whisper of geothermal steam rises through an ancient stove. While in the background, drilling rigs go searching for the geothermal motherlode. There are few places in the world where you could do this, drill right through the crust and plug into the energy.
Quite literally, this is drilling into a volcano to mine heat from the bottom of the Earth's crust.
Yes, and go down 50 meters per day on average, depending on the type of bedrock you have. The length of this hole is more than 2,000 meters. The longest one here is about more than 3,000 meters, and up north they are drilling a hole which is 4,000 meters. And when you consider in these areas the crust is about 5 kilometers, so they're almost through the crust here.
So when people say we're running out of energy, that's not strictly true, is it?
No, not when you, not in the terms of geothermal energy, definitely. As long as we have active volcanoes in Iceland, we will have energy.
What you do at the end of a hard day's doing geology.
Yes, definitely. And I guess Icelanders have been using the hot water since the beginning of settlement, of course. Bathed in it, cooked in it. And this is an excellent example here. The locals needed a pool to teach the kids to swim. There is hot water coming from out of the rocks here. And they just built these concrete walls, and it filled on its own. And this they did in 1923.
So this is from a natural spring of hot water.
It's coming from the volcano above us. 85% of all houses in Iceland are heated with this. We are using this to generate electricity. So it's a big asset for the country.
So it's not all bad news living around volcanoes?
No.
This is one of the rewards?
Definitely not.
Bathing in hot springs, outrunning ash clouds. It's all part of the Icelandic experience. In 1783, when the volcano Laki last went off, lava fountains reached over 1 kilometer into the sky. The ash fallout from the eruption drifted to Europe and pretty much eliminated summer in the UK. The effects of Laki precipitated the Little Ice Age in Europe at the end of the 18th century. All of that landscape to the horizon is lava from Laki. It completely altered Iceland's southern shore.
So we are looking at the lava field from Laki in 1783. The fissure is some 50 kilometers north of us. And the lava flowed down the valley of Skaftartunga and actually followed the channel of Skaftá River. And the first thing that the locals noticed was that the river actually dried up because the lava dammed the river. And then they saw, of course, smoke up north. And then eventually the lava came down here and it spread out on the lowland.
Flowing down from our right to our left.
It's literally a sea of lava, isn't it? The scale is unbelievable.
It is.
And this was the largest lava flow anywhere on the planet in the last 10,000 years.
Yeah.
The gases from Laki poisoned all the farmers' grass and killed off the livestock. 25% of the Icelandic population died.
Yeah.
So this would have been a real scary place in 1783.
Yes, definitely. And after it sort of froze here, it became an obstacle for transportation. Of course, it destroyed a lot of farms. And I mean, there wasn't a decent road going through here until in the 80s. So it's, looking around, you can see all these different forms here in the lava.
Eerie shapes.
Yeah, it relates strongly to the mythology here. People walk across, they see faces, they see trolls. It's not difficult to imagine walking through here in the night.
So this is a place they would have kept out of.
Yeah,
They would
yeah,
have been scared of
definitely.
it. So has this been embedded in the Icelandic culture?
Yeah, I would say so. Yeah, definitely. And in fact, the locals here still talk about the time before the fires and after the fires. It's still a time mark, sort of, for the local history here, even though it was as far back as 1783.
As far as Icelanders are concerned, the whole southern coast could be dramatically altered again with one big volcanic blast. The lava could conceivably pour right over the top of this, one layer on top of another. That's how plates are built, and it's also the reality of life here, a deep cultural understanding that the Earth will behave however it wants, whenever it wants to.
So this is where fiery, red-hot magma has flowed out and cooled quite quickly.
Icelandic legends say this basalt is actually made out of petrified trolls.
Like organ pipes.
Yeah, they are.
It's a very fine-grained rock too, isn't it? I can't see any large crystals in there.
But scientists say these organ pipes were actually made millions of years ago when highly fluid molten rock rapidly cooled and took on these shapes.
The top of the flow is up there and its bottom down here.
And the more rapidly cooling, the smaller the columns. And if it's very rapid, they can wind up forming a cube.
It's a stark reminder of how active the mechanics of the Earth are. Up to the end of the 18th century, man made dogmatic assumptions about his own prominence in the story of the world. It was young and made for him by God. Then the new science of geology emerged, secularizing our understanding of the Earth, taking man out of the center of the story and replacing him with science. The first geologists turned up a tail in the rocks that no one ever imagined could exist. The Scottish capital of Edinburgh is a geological city, if there ever was one. The old part of downtown was built along a high glacial ridge. That's why the Royal Mile is so steep, as are the stone steps that run back and forth between the thoroughfares. Edinburgh Castle sits strategically high above the city, built on the plug of an old volcano that last erupted 350 million years ago. The castle's base is a giant mound of volcanic rock. There's a wonderful Gothic spookiness to Edinburgh. A lot of it has to do with the rock. The Greyfriars Kirkyard is filled with many a stonemason's visions of death. Off in the corner, there's a simple plaque. James Hutton, founder of modern geology. If you weren't looking for Hutton's plaque, you'd miss it. But geologists make pilgrimages to this spot. Hutton was an 18th century scientist who used to make regular hikes around the Salisbury Crags, a big, important hunk of highland geology right in Edinburgh. And it was while trekking here that he came upon his big idea, that the world was born from heat and was much older than scholars said it was. In 1650, James Ussher, the Bishop of Ireland, carefully worked through the Bible and did the math. He determined that creation took place on the 23rd of October, 4004 BC, a Sunday. By the late 18th century, the Earth was almost 6,000 years old by Ussher's figuring, born out of the Great Flood as described in the Bible, until Hutton said the Earth was much older and born out of fire.
Hutton was a farmer, and he was very interested in soil, about the sustainability, the habitability of the planet. And although he believed in God, he argued that God had got the Earth going, and then these cycles based on heat in the inside of the planet resulted in uplift, renewal, and subsidence, and deposition. And so the Earth hadn't been created in a very short time as the dominant theories had it. And then, of course, that completely destroyed, ultimately, the idea that the Earth's surface was a product simply of large floods, Noah's flood. It couldn't be, because rocks had been produced in a molten state.
At the end of the day, he is the father of geology. He was the first guy to realize it wasn't just biblical.
This is called Hutton's section. It doesn't look like much, a seam in the rock just off a footpath. But students come up here from the University of Edinburgh as part of their studies.
It's not that. It's not as impressive as some of the geological outcrops you can find. You know, it's not even as obvious as it could be.
But nonetheless critical.
I think what makes Hutton unique, and what the scientists that we know, the kind of real scientists that make progress in science, they see things that other people have seen, but they see them differently. And I think that's what Hutton did here.
And his big new idea was that some rocks had been formed in a molten state, weren't they? Because the dominant idea at that time was everything was produced by water.
Yeah.
Noah's flood, all that stuff.
Hutton got down in here and realized that two different kinds of rock were blended together, as if one kind was injected into the other. That meant that they had to have been superheated at one time, molten.
And if you go in closer and look at the two different rock types, the top one is made of small crystals, which is typical of volcanic rock, whereas the one beneath it is clearly made of separate particles and clasts and is kind of laminated in a way that the top one isn't. So you've clearly got two different rock types.
And so Hutton's vision was of this being liquid magma seeping in through the rocks and destroying the existing rock, bending and twisting it up. Close to the city of Edinburgh, within just a few hundred yards of his house, here's a great example he can bring people to, and he can say, look, here's evidence that it wasn't just layers on the seabed. Something else has happened here. There's different rocks formed at different times, and therefore the big jump, the Earth is ancient.
After Hutton recorded his section in Edinburgh, he took to the sea in search of more evidence. He had already found that younger rocks didn't rest easily on top of older rocks, but were separated by breaks in the timescale he called unconformities. The story in the layers didn't always make sense, since some of those layers had eroded. They were missing. To Hutton, that meant the old biblical theory was wrong. The Earth could never have come ready-made out of a flood.
So this is where deep time was first discovered.
This is it, yeah. He needed a place to demonstrate it. And you can imagine him jumping off the boat here and finding certainly the best unconformity he'd ever seen, the best unconformity I've ever seen.
And this is where his colleague John Playfair said he felt giddy looking into the abyss of time.
Yes, such a brilliant idea. Because it was such a step forward. We're used now to talking about millions of years and billions of years. But we talk about it without maybe really understanding this great passage of time.
These rocks meant the Earth had a history. The amount of time it took to make these rocks, fold them, break them, stand them on end, and lay new rocks over top was all Hutton needed to prove the existence of deep time.
Yeah, I mean, you get an excellent view here, the unconformity, the strongly vertical rocks here, very coloured, and then the sheets of red rocks on top.
Yeah, it's a fantastic view from here. I mean, you're close into the detail there. The layers on top, the lowest layers of the red sandstone have got bits of the greywacke included. So for Hutton, that was one of the important pieces of evidence from here, the direct connection between the old rocks and the new.
The British Isles are in the middle of the European plate, and they are subject to pressures that come from both ends. This is Hadrian's Wall, just south of the Scottish border. It marked the northern edge of the Roman Empire, and the Romans built their wall here to keep out the Scots.
And it's sort of ironic that the Romans built this wall to try and separate the Scots from the English and try and undo what plate tectonics had done 400 million years earlier. Well, this whole area, we're in the far northern part of England, records the plate tectonic suturing, welding together England, which used to be quite a separate little landmass, with Scotland. And that occurred about 400 million years ago when a previous ocean, previous to the Atlantic, closed, and that's called the Iaptus Ocean. So this area illustrates how the European plate got built. And there's been a whole succession of these little collisions to build up this larger mosaic that we now call the European plate.
That mosaic, though, is subject to an immense amount of torsion. You just need to go and look at cross-sections on the coast of the English Channel to see how intense the pressure can be. Start in Kimmeridge in Dorset. Each thin and delicate wafer of shale here represents a layer of sediment laid down into a shallow tropical sea 175 million years ago. These layers have basically been untouched. They appear as they were created. They're so orderly that geologists can even tell how old these shales are by looking at the types of fossils trapped between them.
Yeah, these are pages. Imagine a book just turned on its edge, and we've got the pages exposed right here in front of us. So as we go up through the pages, we're going through the book, we're going through the chapters, and instead of numbers on each page, we have what we call zone fossils, which are consistent groups of fossils found within each layer. And they may be very small microfossils, such as in these shales. These were muds on the ocean floor, or they may be large ammonites. But either way, they change through time, and by recognizing the distinct form of the microfossil or the macrofossil, we can actually put a relative age on these rocks. We can say this layer is older than one that's younger.
Just down from Kimmeridge, holidaymakers search the bluffs at Lyme Regis for larger fossils. So many fossils have been found in the layers of rock here that the region has been renamed the Jurassic Coast.
Especially for the fossils. It's beautiful.
And no one searches more keenly for Jurassic fossils in Lyme Regis than Steve Davies, who runs his own museum here.
It's just full of them, isn't it? We can see, just looking at this, we've got quite a range of different shapes and sizes of the beasties. But as you go up through geological time in the Jurassic, there are thousands of different species, varying in terms of size and the ribs that grow on it. The coiling, sometimes they're tightly coiled, sometimes they're really open coiling.
So there are important concepts about time and almost barcoding different rock layers by their fossils.
You can recognize distinctions in those ammonites, the zones and the subzones, with a resolution of maybe 250,000 years of time. That's like being able to recognize an instant in our day. It's amazing.
So you can put a rate on evolution itself?
You can do that, yeah. It's the fundamental bit of geology, that you can categorize a body of rock by its fossils and track it across. Same fossils, same rock. You don't need to be thinking in terms of Darwin and evolution and millions of years, just same fossils, same rocks.
Now look at those same rocks down the shore a bit from Kimmeridge and Lyme Regis. Here at Lulworth Cove, the effects of the compression are pretty clear. The question is, where did that pressure come from?
Well, these rocks have been body checked by Africa coming up from the south. Think of a bow wave in front of a huge tanker. Think of Africa as a giant tanker coming up north. So right close to the bow, you've got intense folding in the Alps. A little bit further away, you have smaller waves. But essentially, it's a big bow wave on a giant scale as one continent plows into another plate. And it gently rippled the rocks to give us these folds and the gently rolling countryside. When I first came here, this was in the 60s, and geology was really very much concerned with stratigraphy, the relative age dating of rocks. Rocks are older than these are younger than those, and so on. These are my notes that I made when I was a student of geology, late teenager. We had to keep a notebook where we describe what we saw, and I sat up here and made sketches of these very cliffs. So that's their hole. This is the Lulworth Crumple. These were flat-lying Jurassic rocks, and they've been pushed by African plate coming up from the south. Coming back today and seeing this, I see this in a completely different light. It's not just layers anymore, it's deposits of a now extinct ocean. And I can now put this in a plate tectonic content and look at this in its global perspective. So there's been this tremendous development of plate tectonic science. And the revelation has really been of the recognition that continents come together, they form supercontinents, and then they break up. And that's a sort of basic cycle, maybe 250, 300 million years, maybe a little bit more, of most of Earth history.
So everything is connected tectonically. The edge of England is crumpled by the onslaught of pressure coming from Africa, hundreds of kilometers away. But it is nothing compared to what happened closer to the collision zone, where the mountains are. The Alps touch 6 countries in Europe, including Switzerland. The very term Alpine, which has come to embody all things mountainous, comes from here: skiing, yodeling, and mountain climbing. Geologists see the Alps as more than that. They see a story of tectonic violence and the Earth in the throes of contorted change. Iceland was what they called the passive end of the Eurasian plate. This is the active end.
Shall we? Yes. Go to the top of the Matterhorn.
Geologist Stephen Johnson from the University of Victoria has spent years tramping around the Alps.
Well, what a day, eh? I mean, really.
Yeah, we're very lucky, aren't we?
Yeah.
His specialty is studying the structure of mountains, and he's been working on how the Alps were formed.
Yeah, all of this rock actually was deposited south of the European continent on oceanic crust.
Yeah.
Africa's moving north, and its northern end is colliding with Europe and giving us this mountain range.
Well, the rocks that we see in this lower part of the mountains were, again, marine rocks deposited in an ocean that's long ago ceased to exist. Yeah. Because it was caught up.
It's a pretty safe rule to follow that when continents collide, seas die. There was at one time another sea between the African and European plates. It was called the Teths, but it was victimized by the onslaught of the African plate. It plowed underneath the Teths and then bulldozed into the European plate.
We know that the ocean started to close enough to affect Europe in the Jurassic, so some 180 million years ago. We start to see the European continent bending down, getting flooded by the ocean, and it's being dragged down by this oceanic plate sinking down beneath Africa. And as it sinks down, Africa advances on Europe, and the real collision, though, doesn't start until much later, less than 100 million years ago, probably around 60 million years ago. So it's a long process. The plates only move centimeters, maybe 10 centimeters a year, so it's snail-like compared to the way humans think and the way humans observe.
Yes, go on. Let's go and do some walking and look at some rocks.
An iconic view, isn't it?
God, just amazing. Yeah. You can see why they call a lot of their high mountains dents, teeth.
Yeah. Yeah.
They might look like teeth now, but all of this rock was originally huge blocks after the continental collision. The shifting of the plates caused the blocks to pile on top of each other. Then the glaciers moved in and started sculpting the blocks into the mountains we see today.
Yeah, it's worth remembering, isn't it, that the rocks that make up the mountain are old, but the mountain itself is almost brand new. It's been formed all the time by erosion.
Like how long did it take to make a mountain like that?
Well, it's been cut by glacial erosion, and glaciers have only been in this area for the last couple of million years. So it's a very, very young mountain chain.
Yeah.
Geologists are really storytellers, and they gather their material by clambering over rocks. Steve is following some evidence here that helps tell the story of mountains and plates and lavas and continental uplift, all on one single boulder.
Yeah, what do you think we have here? These are actually fascinating right here. The kind of shapes we're seeing in the rock here. Can you see this this little ridge that runs out here like this?
Yeah, it's a little rim.
Comes, yeah, like a rim. Comes all the way back around. And there's another one here that goes out. I think these are pillow basalts that have been highly deformed.
Yeah, that have been squeezed and flattened.
Pillow basalts are formed by a volcanic eruption underwater. When the lava hits the cold water, the surface hardens into a pillow shape. The presence of old flattened pillow basalts here means that this was once part of an ocean floor, and the makeup of the rest of the rock says that this boulder has been on an amazing tectonic journey.
So this is conclusive evidence of the existence of a former ocean between Europe and Africa.
So this would have been crust sitting under 6 kilometers of water in an ocean. And then you notice, well, it's flattened, but also all of the micas and metamorphic minerals in here, these things have been highly metamorphosed. And in fact, you can see little pock marks in here that are little red garnets. So this is a rock we call eclogite, right?
So this has been subducted down below Africa
to
great depths.
Yeah, maybe 100 kilometers down into the earth. The thing that always amazes me about this kind of rock is how can you take a rock like this down 100 kilometers and then get it back to the surface? It seems unbelievable.
You need to erode a lot of crust on top, don't you? It's a balance between cutting down into the rocks and more rock being brought up and exposed.
Yeah, I think you'd have a hard time, though, with just erosion getting this back to the surface. I think somehow the African plate must act like a bulldozer, and it caught a piece of the oceanic crust and brought it all the way back
It's like
up.
an elevator.
Yeah, yeah.
At just under 4,500 meters, the Matterhorn is one of the highest mountains in the Alps, straddling the border between Switzerland and Italy. The 4 faces point to the 4 corners of the compass. geologist and poet John Ruskin called it the most noble cliff in Europe.
So we're sitting in front of a classic European mountain and icon in Europe, but it's not actually made out of European rock, is it?
Yeah, it's amazing, right? We're sitting on these oceanic rocks down here that were the south margin of Europe, and that whole edifice that is the Matterhorn is again continental rock that sits above all of this oceanic rock. But it's not Europe. It's actually a piece of Africa that's been shoved right in over top of us, back towards Europe.
So it's an African mountain.
It's an African mountain. Yeah, no, it's Italy is actually a prong, a peninsula that sticks off the north margin of Africa, and it's that Italian peninsula that's driven into the soft underbelly of Europe here, and that's the leading edge of Africa, sticking up over top of Europe here.
So that's ironic again. We're on the border of Switzerland and Italy, but we're on the border of the European plate and the African plate, tectonically.
Yeah, that's right, yeah. And how it gets so far in is amazing.
Trying to understand tectonics can make the story of the Earth seem so random. How else can we explain that the most recognizable mountain in Europe happens to be African? But in tectonics, geologists see a sense of order and predictability. They know that the Earth is never truly settled. Even if mountains are only moving a few millimeters a year, they are still in motion.
And before the tunnel, of course, there was a road over the top. And before that, there were tracks.
The St. Bernard Tunnel cuts through almost 6 kilometers of the base of a mountain.
As we're going south into Italy, as we cross the international border, it's very close to the plate boundary too, isn't it?
Yeah, the border between Switzerland and Italy essentially is just about that boundary between the African rocks that have been pushed north over the European plate.
So the tunnel itself was cut right through the plate margin.
Yeah, the Alps still are a very active, seismically active region.
Yeah, which is another problem they had to contend with in building the tunnel, major earthquakes.
Yeah, maybe we shouldn't talk about that right now.
All right.
Before these tunnels made travel through the Alps possible, cultures developed apart from one another in isolated mountain valleys. That's why there are Swiss on one side and Italians on the other.
Yeah, I'm always fascinated by the extent to which mountains have shaped human history. Amazing, eh? Different rocks, different fauna.
Feels like Africa.
Smells like Africa.
Actually, there should be a big marker up somewhere, shouldn't there? Saying you have crossed from Europe to Africa.
It's amazingly warm compared to the north side of the Grand St. Bernard Tunnel.
Yeah, this warm air coming up from the Med has a noticeable effect on the climate. You see the snow lines much higher, there's much less snow.
Than on the Swiss side.
Yeah. So there are fewer glaciers on the Italian side, they're higher and smaller.
You can still see all the rocks actually descending into the earth away to the south.
Yeah, this is all still African crust, isn't it? But it's been pushed up.
So this is all still stacked up into the Alps, pushing up and over European crust.
Well, we have to go back through the tunnel to see that old European crust thrust up.
Yeah.
So we should do that.
Head back north.
Yeah.
Just as soon as I'm finished my coffee and grappa. Cheers.
When Nick was still in the UK on this journey, he said that a continent is like a mosaic, and mosaic might still be the best term to describe the composition of a continent. From the majesty of the Alps to the geologic rippling of the UK to the volcanism of Iceland, it's a great story. The thing is, the story isn't finished. It never will be. 200 million years ago, Europe didn't look like this, and in another 200 million years, these vistas will be gone. Tectonic plates, by their very nature, have to keep moving. We just live on them at the Earth's discretion.